The aim of this work is to generate explanations for neural networks prediction by identifying a minimal subset of input features critical to the model's prediction. Our proposed method addresses two major issues: scalability of SMT solvers to deep neural networks, overcoming out-of-distribution inputs issue, which is seen in perturbation-based saliency methods. SMT solvers are routinely used for symbolic modeling and verifying correctness of software programs, and more recently they have also been used for verifying properties of deep neural networks. Model explanation is one such domain where SMT solvers have been used but have been limited to very small size networks. In this work, we address the issue of scalability of SMT solvers by leveraging gradient information, thus enabling their usage for different applications. Model explanation deals with identifying and highlighting input features relevant for neural networks prediction. A lot of the existing saliency methods generate such explanations by perturbing the input and analyzing the change in the final layer activations. Since the perturbed input is often out of distribution, the generated explanation isn't much reliable. We wish to fix this problem in our proposed method. The first step is to use integrated gradients to identify nodes in the first layer that capture information relevant for the prediction. Then a minimum mask is found, which retains a fraction of the activation of these nodes. Since our method doesn't do a full forward pass of the masked image till the final layer, the out-of-distribution issue is mitigated. Also, this approach is scalable since it eliminates the need to encode the full neural network. In the next slide, we explain the core intuition behind our work. We name our method Smug because it uses gradients to reduce the size of the symbolic encoding, thus scaling the SMT solvers to analyze deep networks. Let's see how Smug works for this neural network. For given input, we treat the first layer activation as an input to the subsequent network and use IG to score the neurons based on how much relevant is the information being captured by them in regards to the model's prediction. Then we restrict our analysis to the top k neurons chosen on the basis of saliency scores. The set of input features associated with these neurons are deemed important. However, this set of features might contain false positives, and hence we introduce a notion of minimization where we aim to filter the less relevant features. We symbolically encode the chosen neurons and find a minimal mask such that the masked activation retains a fraction of the original activation. The hyperparameter gamma regulates how active the masked activations are. Thus, we define relevant features as a minimal subset of features in input that causes these nodes chosen using IG to remain active. The notion being if for a masked input, the important nodes are active, then the mask contains the information deemed important for the prediction of the original image. We run experiments on inception model trained on imaginary dataset. We set top k equals 3000 and gamma equals 0. As we can see, the saliency maps produced by Smug are much more crisp and sparser than Smug base and IG. We evaluate a saliency map quantitatively by using the LSM metric, which converts a continuous saliency map into numerous binary masks by using thresholding. Then the tightest crop is found for the given binary mask. Finally, the confidence of the classifier on the cropped image and the crop size are used to compute the LSS score for each mask, and the maximum score is reported. The negative the LSS score, the better the saliency map. As we see, Smug outperforms all of the baselines. As we'll discuss later, Opbox achieves a very negative score by gaming the LSM metric, and its explanations aren't faithful to the model. Smug and Smugbase achieve similar LSS scores, even though the former produces much sparser saliency maps. It's because the LSS score considers the size of the cropped region as a proxy for sparsity. Furthermore, the similar LSS scores signify that Smug was able to retain the important features even after minimization. Here we observe that the cropped region for Smug and Smugbase are pretty much the same, even though Smug's saliency map was much more sparser than Smugbase. Opbox employs a brute force search to find a cropped region which achieves the best LSS score. We conduct an experiment to show that by doing so, Opbox tends to identify redundant features which are packed tightly in a small region. In this example, the presence of the bigger cat makes the smaller cat redundant. A good salience map should thereby assign higher attributions to the bigger cat. Smug and IG do so, but Opbox attributes the prediction to the smaller cat instead of the bigger cat. Finally, we also run experiments on text data and show that our method is also applicable for the text input.